I'll just do A1 real quick then too. Right, and so this one asks to list 3 ways to increase the reaction rate and explain why they work using equations or examples, right? And so one of them is temperature, right? And so the reason that that works is if we pull up the Arrhenius equation, right, the rate K, right, the rate constant, that's equal to A to times the exponent times EA over RT, right? And so part of that, part of the K value, right, is dependent upon the temperature. So the reaction rate is dependent upon the temperature in that case, right? The K values are always going to be different at different temperatures in those cases, and you can measure them out at one temperature, right? And you can measure them out at a different temperature, and then hopefully, you can use that information to get what the activation energy is, and the activation energy, right? You can kind of like plot things, and you can figure out what everything is in those scenarios. But temperature is one way that you can increase the reaction rate. Another way that you can increase the reaction rate, right, is you can increase concentrations. Right, so aside from zero order reaction rates, which the only thing you can really do there is temperature, right? But for first order, second order in those cases, right, the concentration is always going to be equal to, the rate constant times the concentration is always going to be equal to the rate, right? So if you increase the concentration, right, the rate of the reaction is also going to speed up in those cases. So that's an important thing that you can use in those scenarios. And so then the final thing that you can do in these scenarios is you can add a catalyst, right? And I don't know if you guys necessarily went over catalysts in class, right? But the way that catalysts work is if you have like a reaction, and let's just say, right, it's like, you have something like this right here. You have to overcome this energy barrier, right? So that right there is the activation energy. So that's where, right, like adding heat and so forth, right, kind of helps out with speeding up the reaction rate, but you still have to put in a lot of stuff, right? You still have to overcome that energetic hump. So what a catalyst does, though, is the catalyst takes your points, right, and it adds basically intermediate steps that have lower activation energies in those scenarios. And so by lowering the activation energy, right, you're going to be increasing the reaction rate, right? That kind of goes back to the Arrhenius equation. And so even though it's not the most straightforward pathway, right? It's like, instead of going from point A to point B, you're going, from point A to point C to point D to point F to point B in that scenario. It may just very well be, right, that it's a lot faster that way because it's, a lot quicker, right? It's kind of like, I guess like an example, right? The most direct way, right, between, like, you can walk from Providence to Boston. But one thing that you could do too, right, is hypothetically, is kind of out of the way, right? But let's just imagine that I-95 doesn't exist, right? You could drive up to Worcester, right, in a car or something, right? But that's the only way that you can drive with a car, right, would be to Worcester and then to Boston. But that'll go a lot faster than if you were walking straight. So even though, right, you're going to be adding, I don't know, 30 miles or whatever to the thing, if that's the only way that you can drive it, then that's going to be a lot faster than if you were to try and walk directly between the two of them.